Without further ado, I would like to introduce our next speaker, Dr. Shen Yu. Dr. Shen Yu is a PhD student from the Department of Industry Systems Engineering and Management, National University of Singapore. He will deliver a speech on network resilience of port infrastructure and processes. Please join me in welcome Dr. Shen Yu.
Good morning, everyone. I'm Shen Yu. Currently, I'm a PhD student supervised by the late Prof. Li and Prof. Chu. I'm from the Department of Industrial Systems Engineering and Management from the National University of Singapore. Okay. Today, I'm going to share with you some general ideas on my research topic, the network resilience of the port infrastructure and processes. Before I get started, I would like to acknowledge the kind support from the Center of Excellence in Modeling and Simulation for Next Generation Port and the Singapore Maritime Institute. Okay, first of all, I would like to introduce a basic definition of key word called the resilience. I will introduce the resilience in two perspectives. First is an inherent ability to withstand the disruptions event with little loss in function. And another could be held by other recovery actions. It is the ability to rapidly and efficiently restore functionality if the loss incurred. So why we choose port? Because port is very vulnerable to multiple disruption events. Because it has open, expansive facilities with multiple means of access, both by land and sea. So the port plays quite an important role as a terminal of the intermodal freight systems. And we would like to introduce an indicator to will describe the performance of the port network under different disruptive scenarios, and also help the decision maker to assess their investment strategy or even their reserve security tools. Okay, here is the general framework of my ideas. Before the real disruptions happened, we will have something that in advance to do. We call it as the preparedness. After the disruptions, we also have the recovery actions to help to mitigate the impact of the influence of the disruptions. The disruptive event could be multiple types. It could be the natural, like the extreme weather. It could be even a malicious attack, and even some small errors like the technical or accidental human force. So here I generated 5 kinds of the disruptive scenarios from the past literature. They are different in terms of their impact magnitude, their range of the influence on the network. Generally, the influence are totally based on the reduce of the link capacity and also the decrease of the traversal time of the OD pairs. So, like I mentioned before, I want to have a performance index to well describe the performance on the different disruptive scenarios. So I defined the so-called the port resilience alpha as the ratio of the expected post-event total demand and pre-event total demand. The general problem is formulated as a two-stage stochastic mixed integer program. The one state is the preparedness, and another stage, the second stage, is the after-event, post-event activities. So because the below part is a fixed value, so we only want to maximize the above part of this formulation. And it is also subject to several constraints, like the total the demand constraint, the link capacity constraint, traversal times budget. So we care not only about the time budget, but also the monetary budget. We also have other constraints, like the actional operation limitations, binary and integrality constraints. Okay, because we would like to gain as good as possible solutions in a limited times, because sometimes we need to make the real-time decision. So I introduced a solution technique, improve the solution techniques by the methods of so-called Lagrangian decomposition to improve the computation time. So the general idea is to relax the coupling constraint, which it is a complicated constraint, into the objective function by the Lagrangian relaxation approach, and decompose the original problem into two sub-problems. And the first problem is, the first problem can be considered as a minimum cost shortest path problem, while the other one is just a traditional optimization problem with pure binary variables. So the upper bound can be generated by solving the Lagrangian decomposition problem, and the lower bound can be generated by searching for the feasible solutions. If the upper bound is just happen to be equal to the lower bound, then we can see the optimality will be achieved. In order to update the Lagrangian multiplier to reduce the gap, subgradient optimization algorithm is used. Here is the framework of the algorithm. I will not go inside of the algorithm itself because of time limit, because of the time budget. Yes. The following slide, I will introduce how the model works in practical problems. Here it is the input data of this model. We have the first picture is the network data, and the second picture is the OD pair data, and the preparedness and the recovery actions. The preparedness have 4 dimensions, while recovery actions has 3 dimensions. They have general patterns in terms of the like add-on capacities, to increase the traversal time, and to also it has a time for itself to execute itself. Okay, the large-scale experiment shows a good improvement in computation times compared with the original problems. I compared with the results in terms of the number of the scenarios, and also the number of the pre-actions and the post-event actions. I also compared the results with different number of OD pairs. You can see I can gain as good as possible solutions in a limited times. So you can set the acceptable level and to check whether it achieves your goals, your aims. Okay, I also have done some preliminary numerical case studies. I did the experiments based on the resilience level on the different budget levels, also the experiment based on resilience by different strategies. It is obvious that as long as you get sufficient funds, get sufficient monetary budget or time budget, you can achieve as high as possible performance index, the resilience you want. But I would like to highlight that the key ideas on that we do not pay too much attention on the resilience index itself, but on what actions to be chosen from your toolbox. So the real idea on this model is to decide which actions to be taken before the real disruptive event and what recovery actions to be taken after the event. So to conclude, such a detailed network representation permits the operators to examine their recovery toolbox, including the preparedness and recovery actions. In my model, the preparedness is treated as a buff to post-event actions, and all the recovery activities can be initiated in the short term to mitigate the disruption efforts. So the only limitation is, like I mentioned before, the time budget and the monetary budget. The resilience measures reflects the effectiveness of the recovery toolbox given a recovery budget. The model can provide insight into whether the recovery budget is adequate to implement needed recovery options. Also, the work could be applied to other more complex infrastructure-related network. And my future work will, based on these, will continue to research on the impact of different disruptive scenarios. Also to study on the potential impact on the disperse of the influence of different disruptive scenarios to other supply chain clusters, or even more specifically other ports, to see how the other ports operate while their neighborhood is suffering from the disruptive event. Okay, I think that is all for my today's presentation. Thank you very much.
There is a question for you on the pigeonhole.
Okay, sorry.
Let's put it alive.
Yes.
Yeah, so I think the question is on how do you validate your research outcome, right, against real-life disruptions. So is there any plan to look at how your mathematical model could be validated in real-life scenarios?
I think that is a very good question. How to validate my result? So far, I think that there is no very good method, or I haven't thought of that before. Maybe we can use a simulation-based method to compare with the result with my model outcomes, with the simulation outcomes. I think that is a good method based on that, because disruptive event is a low probability happen. So, which means we cannot gain sufficient data from the real practical problems. So simulation, I think it is a good method. But in my model, I haven't done something like that. Okay.
Yeah, thank you. Any questions from the floor? We still have about 3 minutes for any quick question. No? All right. So thank you, Shen Yu.